This lecture is a discussion of how the resistivity of a material is actually temperature dependent. And so what I'm going to end up showing you in this lecture is something of an analogy with a dance club, and also a very simple model of the resistivity's temperature dependence. That is, we're going to write down a function for resistivity as a function of temperature. But you should take that strictly as an approximation. Okay, so resistivity is given the symbol rho, and it describes how difficult it is for a conduction charge to find a free path within a material. And the way that we defined the resistivity is, let me erase that. We said that you're going to get a current density through the material because of electric field, and the proportionality is 1 over rho. So the larger the resistivity value is, the smaller the current that you're going to get. Okay, but what I'm going to show you, right, if you look at the title, the resistivity, this thing rho, is actually a function of temperature. And roughly speaking, for many materials, as the temperature grows, the resistivity also grows. All right, so here is an analogy, right? And the analogy is with walking through a large crowd of people at a dance club. So here are a bunch of dancers, right? People hanging out, talking to each other, enjoying each other's company at a club. And you are a little person. I'll draw you in red. And you are on one side of the club, but you would like to go to another side. You have some sort of compulsion to cross the crowd. It's as if there was a field that caused you to want to say, go to the bathroom or leave the club. But as you try to walk through, you'll be encountering people who are sort of constantly getting in your way. And even though you have a goal in mind and the fastest way to get there is a straight line, you're going to drift through the crowd in something of a random path, depending on what shows up in your way at the specific time. And even though maybe you really do need to go to the bathroom really bad, so you have this force compelling you to accelerate through the crowd, you only can manage basically a drift velocity. And if you remember, J, that current density, is proportional to this drift velocity. So that means that the drift velocity, which is associated with J, is also connected to the electric field, as well as 1 over the resistivity, which I'm telling you is temperature dependent. So as you try to pass through, you constantly have to divert your path. As people move into and out of your way, you speed up and you slow down. There's all kinds of accelerations and interactions, but you end up drifting through the crowd at some basically constant speed because the crowd is resistive. So here is where the analogy really kicks in. As you are crossing the crowd, if the music becomes more exciting, as if the DJ turns up the temperature, and the people are going to dance a little bit more wildly, larger amplitude of oscillation, etc., right? The people that are in your way are going to be more often in your way, and it's going to reduce your drift velocity. And if your drift velocity reduces, that's your current density also reducing. And if your current density reduces, but you still have the same compulsion, you still have to use the bathroom the same amount, that must mean that the resistivity changed. And that's what we're going to say. we're going to say that as a function of temperature, the resistivity has some sort of shape that tends to, like, as it becomes hotter, right, as an object becomes hotter and its nuclear centers move around more erratically and covering a larger distance, the resistivity is just going to climb. And the idea is, this is how you connect the dance club analogy to the physics we're trying to describe. We say that the conduction charges, as they pass through the material, they're passing amongst all the stationary nuclei. Remember, the positive charge centers don't get to move. But the nuclei aren't actually stationary. Rather, what they do is they move around like this. They move around their center back and forth, and they do it more and more wildly the bigger and bigger the temperature is. That's actually what the meaning of temperature is. Temperature is associated with thermal motion, random thermal motion. So the higher the temperature, the more active is this network of people that you have to pass through, which makes that network of people more resistive because you have a reduced drift velocity. So what we're going to do is we're going to model the resistivity this way. We're going to say that the resistivity as a function of temperature, it's going to be equal to, and this is going to be kind of a weird way to say stuff, but we're going to say that there is a sort of starting point value or a base value. I'll show you what this means in just a second. There is a slope. There is a temperature difference. So this doesn't mean proportional. This is a symbol called alpha. And then there is our reference value. So let me make this symbol more clear. So it's a number called alpha. So alpha is a description of the temperature dependence of the resistivity. But check this out. What if you evaluate what's the value of the resistivity at some temperature referred to as T sub 0? It's equal to some rho sub 0 times alpha times 0 plus rho sub 0, which is rho sub 0. All this is saying is we're saying that the resistivity at T0 is rho 0. So here is some example data. I'm reading this from a chart from a textbook. So here's an interesting thing. Silver. So silver is atomic symbol Ag. It has, let's see, resistivity rho. It has a value of 1.62 times 10 to the minus 8. And it's in units of ohms times meters. Remember, the ohm meter is the unit of resistivity. So that's the value of the resistivity. But silver has what's called a temperature coefficient of resistivity, which is called alpha. And alpha comes with the units of the inverse Kelvin. So the Kelvin scale is the temperature scale that's appropriate for this formula, or at least for this data, actually. And this alpha value for silver is 4.1 times 10 to the minus 3. Right? And so this data table, let me remove this examples designation. So this is data for temperature equals, so 20 degrees Celsius, but I'm telling you that alpha is written in terms of inverse Kelvin, and the 20 degrees Celsius is the same thing as 293 Kelvin, right? So Kelvin temperature. That means that this right here is rho naught if T sub 0 is 293 Kelvin. That's the idea. Another example, which is really interesting though, and this is just another conducting material. Actually, just for some difference, let's put in a different material. Here is, how about tungsten? Tungsten is a material that people use to make light bulbs, old light bulbs. A tungsten alloy filament light bulb, Thomas Edison style light bulb. So tungsten has a resistivity of about 5.25 times 10 to the 8th. Whoops, not 10 to the 8th, 10 to the negative 8th. So it's a really small value, right, for resistivity. That means its conductivity is very large. It's a very good conductor. But this tungsten actually is, 4 or 5 times resistive compared to silver. Its alpha value is 4.5 times 10 to the minus 3. Right, same units, inverse Kelvin. But here is a very exotic material. Here is pure silicon. And the interesting thing about silicon is it's actually not a good conductor. It's got a very, very high resistivity. And its value of resistivity at 293 Kelvin is 2.5 times 10 to the 3. Which means, if you look at this, 10 to the negative 8, 10 to the 3. 10 to the 3 is 10 to the 11th times as big as 10 to the minus 8. That is, this is 10 to the 11th times more resistive than tungsten. Pure silicon is more like an insulator. And this insulator, though, it has a very interesting alpha value. Its alpha value is negative 70 times 10 to the negative 3. So why the negative? So this is interesting. It's saying that if you were to look at rho as a function of temperature for silicon, as a function of temperature, as the temperature goes up, the resistivity goes down. It's a negative slope. Whereas these over here, if you look at the resistivity versus temperature, they're positive slopes. They're really small, and this is actually really small as well, but they are backwards to each other, right? The negative sign is important. Okay, so this right here is a model of the temperature dependence, and it is an approximate model. And you as an engineer would go and look in tables of values for alpha and also for rho sub 0. But what you would do is you'd make sure that as an engineer, you need to know the resistivity very close to a particular temperature. So some people might be worried about 293 Kelvin, which is like room temperature. But other people might be more worried about 5 Kelvin, which is really, really cold. Others would be more worried about 400 Kelvin, which is just before the melting point, say, of something. Yeah, I think you know what I mean. So as an engineer, you'd want to know the alpha value nearby the temperature in which you are using or trying to understand the electrical conductivity characteristics of your material. Yeah, so, all right, that's it.